Hello and welcome to my tutorial on derivations of geometric formulas. Today we will be discussing the formulas for the circumference of a circle and the volume of a cone, and we'll be deriving these with calculus concepts. Alright, so first we're going to do the circumference of a circle derivation. And just as a reminder, for those of you who for some reason forgot, the circumference of a circle is equal to 2 pi times the radius of that circle. Alright, so we're going to set out to prove that the circumference equals 2 pi r. Now, first, I'll show you the unit circle. And as you can see, there is a circle with a radius r, and any point on the circumference on the edge of the circle can be described in the form x, comma, y, with x and y and r as defined there. So, using that information, we know that by the Pythagorean theorem, x squared plus y squared equals r squared, which can be used to describe any point on this circle. And solving that for y, we get the equation y equals the square root of r squared minus x squared. Now, if we differentiate that, if we differentiate y with respect to x, we get the equation dy by dx equals, and don't forget we have to use the chain rule on r squared minus x squared, so dy dx equals negative 2x times 1/2 times 1 over r squared minus x squared. And if we eliminate the 2's, we get dy dx equals negative x over r squared minus x squared. Now we are going to apply the arc length formula, which you could see as follows. S, which is the arc length, equals the integral from 0 to r of the square root of 1 plus dy dx squared dx. So, for now, we are going to be taking the arc length of just one quadrant of the circle, and that's just to make the limits easier and all that kind of stuff. So, we're going to start. The arc length of one quadrant of the circle is again the integral from 0 to r of the square root of 1 plus dy dx squared dx. But we found dy dx in our previous slide. So, we could substitute that in for our equation for arc length to get s equals the integral from 0 to r of the square root of 1 plus x squared over r squared minus x squared. However, we all know that, unfortunately, we cannot integrate that easily. So we're going to have to put it in terms that are more easily integrable. So, in order to simplify what is under the radical, we have to find the least common denominator. And because 1 is 1, we know that the least common denominator is r squared minus x squared. So we could simplify the arc length formula into s equals the integral from 0 to r of the square root of r squared minus x squared over r squared minus x squared plus x squared over r squared minus x squared dx. And that simplifies furthermore, since the x squareds cancel out, into s equals the integral from 0 to r of the square root of r squared over r squared minus x squared dx. Now, we're going to integrate. But first, we can simplify this equation a little bit more. As you can see, there is an r squared on the top, and since there is a radical over it, it turns into an r. And since r is a constant with a circle, we could take that out of the integral. So we end up with the arc length equals r times the integral from 0 to r of dx over r squared minus x squared. Now, what does this look like? What formula does this look like? Well, it looks like the arcsine formula. So if we integrate using the arcsine rule, we get s equals r times the arcsine of x over r evaluated from r to 0. R to 0. And if we evaluate those limits, we get s equals r times the arcsine of 1, which is r over r, and the arcsine of 1 is pi over 2, minus the arcsine of 0, which is 0. And we can simplify that down into s equals pi r over 2. Now, you may be wondering, that is the last step. We can't really simplify that anymore. But remember, the s we were solving for is only one quadrant of the circle. In order to find the circumference, we have to multiply that by 4. So the circumference equals 4s, which is 4 times pi over 2, which, of course, yields the equation c, the circumference, equals 2 pi times r. And that is the derivation of the circumference of a circle equation. Now, we're going to derive the volume of a cone formula, which is shown right here. The volume equals 1/3 times pi r squared times the height of the cone. Alright, so first we can't really start finding out the volume of a cone until we find our differential volume. Now, looking at this diagram of a cone, we see that the volume of a cone is simply the sum of the volumes of disks with an infinitely small height dy and radius x. So therefore, the volume of the whole cone is the integral, the sum of all these different differential volumes as shown by these little disks, where a differential volume equals the volume of a disk, which is pi x squared dy. And as you can see here, there is a diagram of these disks. So, the pi x squared comes from the area of the circle that is located on top of the disk, and then the dy, again, creates the thickness of the circle. And overall, pi x squared dy is your dv. Now, as you can see, there is still an x and a dy, and you can, and both of those variables are changing as the radius increases and decreases in this cone. So we are going to have to put x in terms of y. And we can do that using similar triangles. So in order to integrate, we have to express x in terms of y. And by looking at the vertical cross-section of a cone with radius r and height h, similar triangles are created at different radii x. The sides of these triangles are proportional by the AA postulate. So therefore, x over y equals r over h. And we can simplify that, solving for x, to get the equation x equals r over hy, and a reminder that r over h are both constants. So we have x in terms of y now, so we could substitute this in for x in the dv equation we had on the last slide, so we get the following expression for a differential volume. So dv equals pi times r over h times y squared dy, which then, if we distribute the squared, we get dv equals pi times r over h squared y squared dy. And that we can integrate over. So now we're going to do the integration step. So in order to find the expression for the total area of a cone, we must integrate the differential volumes with respect to y from y equals 0 to y equals h. By doing this, we are adding up all the volumes of the disks with height y and radius x as the height approaches the value of h. So again, we're going to keep adding up disks as they get slightly smaller and smaller until we get to height h, the point of the cone. And that is expressed here. The volume of the cone equals pi times r over h squared, and reminder, those are all constants, so we can take them out of the integral, times the integral from 0 to h of y squared dy. And if we integrate, we get the formula, the volume equals pi r squared over h squared times 1/3 y cubed evaluated from 0 to h. Now, if we evaluate those limits, we get the volume equals pi r squared over h squared times h cubed over 3 minus 0, because if we substitute in 0 for 1/3 y cubed, that all cancels. Now, as you can see here, the h squareds both cancel, so we are left with the equation for the volume of a cone, which is 1/3 pi r squared times the height. And there you have it, the derivation of the formula for the volume of a cone. Alright, now thank you so much for watching. If you like this video, please leave a like and a comment, and be sure to subscribe to my channel, JJSINTX. Thank you. Bye-bye.